Well, the oceans are the surface's largest carbon reservoir. They are absolutely fundamentally important in regulating carbon transfer throughout Earth's surface processes, and obviously regulating atmospheric carbon dioxide levels as well.
Welcome back to the National Oceanography Centre's Into the Blue podcast, where we talk to the people leading the way in raising the profile of the ocean through research, exploration and advocacy. We hope you enjoy today's episode. Before we get into the main subject of the episode today, I wondered if you could give us a bit of background, maybe your career journey to NOC, what your role is at NOC and things like that.
Sure, yeah. So I'm a marine geochemist here at the NOC, and I've been here just over a decade now. So we're in January 2025, just past the 10-year mark. I started life as a geologist, mainly looking at how Earth system processes have responded to climate change throughout Earth's history. That obviously kind of drove an interest in what are the responses, what happens in the oceans. That's our record when we want to look into the Earth's past, but also kind of better understanding of, how might those processes then sort of kicking in the future? Because as we all know, we're seeing right at the moment, there's impacts of climate change are very real, and Earth responds in certain ways. Trying to pick out how that happened and has happened in the past requires certain new proxies, certain techniques that we can use to explore what's been happening. And I really sort of spent a lot of time developing this techniques, understanding that in past episodes or intervals of global warming, the Earth has got warmer, it's got wetter, things have weathered and reacted more quickly. And sort of piecing that together has led me to say, well, actually, can we use some of those techniques nowadays to sort of start to tackle climate change? And that's led me to the work that we're going to be talking about today.
Cool. So can you tell us why you're interested in carbon dioxide removal?
Yeah, absolutely. So climate change is real. It's happening. We know it's happened throughout Earth's history, and we know that nowadays the human actions, emissions of carbon dioxide and other greenhouse gases are really accelerating and driving those processes, that impact of climate change. So what we need to do is to combat that is we need to start sort of removing carbon dioxide from the atmosphere. But if you sort of think of the floodgates are open, we're filling up our bath and the bath is overflowing, you're not going to start bailing out the bath if the taps are wide on. So the first thing we need to do when tackling climate change is stop filling up that bath. We need to turn the taps off and stop emitting fossil
That's a great
fuels.
analogy, by the way.
Yeah, it's an easy one to think of because, you can't fill up a bath and say, well, what we're going to do with all this water if you're still filling it up. So we need to turn the taps off. And then you've still got your bath full. So you've got to empty that water out. And you've got to put that water somewhere. So carbon dioxide removal is one of the processes that we will need to help get the Earth back to the sort of stasis that we have been. Of course, there's questions about how far we go, what we do, what is a stasis. But we need to consider where that CO2 is going, where we're going to put it. And particularly in the context of the questions we're looking at is what are the impacts of putting it into different places? Okay. It's all very well if you're bailing that CO2 out, then you're taking it out of the bath. If you're just chucking it on the floor, then it's not really having any difference anyway to what it would have. So we need to understand what the impacts would be, where it's going to go and how it's going to help us in the long run. And we can talk about this in a second, but there's lots of different approaches being put out there. Some are going to be effective, some aren't. So we need to kind of really do some interrogative work on those assessments. Yeah,
absolutely. And what's special about the role of the oceans in regulating atmospheric CO2?
Well, the oceans are the surface's largest carbon reservoir. They are absolutely fundamentally important in regulating carbon transfer throughout Earth's surface processes, and obviously regulating atmospheric carbon dioxide levels as well. So I'm sure people are familiar with the concept of ocean acidification, that as we're putting more CO2 into the atmosphere, that is correspondingly driving a drop in pH, is driving the acidification of the oceans. And that happens because the oceans naturally absorb carbon dioxide. Now, what we're seeing as a result of that is actually that the oceans have already taken up about 25%, or well over a quarter of the atmospheric CO2 that we've put into the atmosphere. Right. And so they're fundamentally important. It's just a natural reservoir, a natural sink of that CO2. And the process that this happens by is something that we're looking at accelerating in the way that we've accelerated the rate at which CO2 goes into the atmosphere. Of course, the other concept, or the other reason why the oceans are so important, is the size. We live on a blue planet. If we want to tackle the atmospheric carbon dioxide issue, then we're going to have to use the oceans in some way, shape or form, because they are going to naturally act as a equilibrator in our dealings with this.
And for carbon dioxide removal in general, I guess you can marine carbon dioxide removal is only one component. It's happening. There's lots of other suggested areas that they're tapping into as well, I guess.
Absolutely, yeah. So again, I started working in this area and looking at enhanced rock weathering, and still very active on this space. There's a concept of actually crushing up silicate rocks, mainly basalt, but other minerals have been approached as well. You can put that onto croplands. You can put it into other settings where it actually offsets the need for fertilizers, because as it dissolves, it releases those nutrients. Of course, there's direct air capture. There's a biochar, which is kind of burning, locking up carbon in different forms and then shutting it away so it can be stored over longer timescales. There's a heap of different approaches put out there, all of which have pros and cons. Some are very effective, and we're still understanding others' effectiveness. Some have high energy uses, some are lower. There's going to be, there's a kind of phrase, no silver bullet to this. We're going to need to apply different approaches in different settings. Land-based approaches have conflicts with human use, obviously. They can act as beneficiaries, but they may have conflicts in terms of other potential land uses, and there's question marks over our ability to co-apply approaches, particularly where they want to be used in the carbon markets. Who gets the credits, what are the impacts and associated monitoring requirements. Again, as a scientific community, we're still trying to better understand these different approaches. What we're trying to do now in the marine CDR space is to sort of bring that up to the same level as the terrestrial space. It's far easier for us to work on land. We can go, we can see, we can monitor. It's in our backyard. Oceans are not always in our backyard, but they are vitally and fundamentally important. So we're trying to bring that up to the same level.
And what kind of processes are being proposed for marine carbon dioxide removal?
There's a lot of different approaches. I think every time I sort of open up the papers, there's a new one coming out there. Fundamentally, we can boil it down to two key approaches. One is biological, and one is abiological or chemical approaches. Biological approaches, as the name suggests, are related to biological fixation of carbon dioxide, and this is mainly through photosynthesis, where whether organisms or seaweeds actually incorporate the dissolved CO2 in seawater, lock it up into their tissues, and then that CO2 in those organic material will be locked away either by burial at depth in the oceans, or you can actually extract it and put it on deserts or somewhere where it's well out of the way and isn't going to degrade quickly. So that kind of biological fixation removes the CO2 from the seawater. It creates then a disequilibrium between the surface water where the biology has been living and the atmosphere above it. And then that encourages the absorption of atmospheric CO2 into the oceans. The other approach is chemical approaches, and they work in a very similar way in that they extract or increase the potential of seawater chemistry to absorb the atmospheric CO2. So you can do that by adding alkalinity, which is essentially creating, offsetting the effects of ocean acidification. So where CO2 naturally absorbs in, if you add an Alka-Seltzer, the same way as your tummy does, you kind of settle it down, you balance the pH, and you give the oceans more capability to absorb CO2. The other way is to actively extract or remove the CO2 that's already dissolved in the oceans. You can do that electrochemically or by addition of bases, and again you give that ocean more potential to absorb the CO2. So they're the key approaches that are being formulated, and there's various different techniques that have been put out to sort of facilitate that. I'm sure you're familiar with fertilization, iron fertilization. There's been some experiments back in the 90s, and it's being looked at again today. Seaweed burial, enhanced growth and deposition, extraction, kind of some of the key biological approaches. Abiologically, there's direct ocean carbon capture and storage, which is electrochemical approaches for extracting the CO2, ocean alkalinity enhancement for enhancing ocean alkalinity. So there's lots of different routes we can do this, and we're still trying to sort of piece together which is going to be the most effective. There are some other techniques out there, physical approaches where you can forcibly pump essentially the sort of CO2 saturated fluids at the sea surface down. Again, uncertainties perhaps about what that is surface water is being replaced with, just drawing out CO2 waters from elsewhere, and mineralization and other approaches as well. But today it's really the biology and chemical approaches that are dominating.
And I imagine there's lots of research in this space at the moment. And I hear that you're working on a project called CO2 CDR. Can you tell us a bit about that?
Absolutely. So this is a project that's been running for about a year and a half now.
Okay.
So we're kind of got over our initial sort of setting our ground phase and we're really up and running. So the project is strategies for the evaluation and assessment of ocean-based carbon dioxide removal.
Okay.
A bit of a mouthful, but CO2 CDR for sure. So I guess as the name implies, this is about understanding the routes for monitoring and evaluating and really kind of understanding which of these marine carbon dioxide removal approaches are going to work. And it's come at a critical time in the field, is that we know there's a need to conduct atmospheric CO2 removal. We are pretty certain that we know the oceans are playing a fundamental role already, and that they can play a critical role in facilitating the achievement of those net zero targets. But we just don't know what the effectiveness would be of these techniques, what the impacts, how to monitor and measure them. Are they going to be cost effective? Are they just completely, going to be non-viable in terms of the economics and the technologies that we have at present to facilitate what we want to achieve with them? So this project is sort of there to sort of create that understanding, and we're doing it through three core pathways or themes. The first theme is prioritization. So can we improve our understanding of the costs, the economic assessments, the life cycle assessments of basically how much CO2 we emit by doing this process? If you're going to involve ships and mining and crushing and applying alkalinity over the oceans, maybe it's not going to be as effective. But if you're doing it in initial environments where there's already infrastructure, maybe that value, that benefits become much more efficient. Similarly, how are we going to monitor these? We know, and colleagues here at the NOC have been spending an awful lot of time, many decades in fact, trying to observe the oceans. As a scientific community, we know we can measure these parameters and we can do it very well. We can fit that data into models. But are those models and those measurement parameters what the carbon markets need, what the regulators need to see if we're going to sort of start doing this again at a potentially a global scale? So how do we do that MRV, monitoring, reporting, verification piece? The second core theme that we're focusing on in this project is the governance structures. Because it's all very well sitting here as a scientist saying, this technique works, this is great, we have this potential. And then people say, well, hang on a second, what about my community? What about this impact? What about the relevance to us? And we have to do that in tandem with the development of the techniques, because there's absolutely no point in saying, well, it will work if we do it in this patch of the ocean, and then we find there's a conflicting industry or use of that ocean space. So we have to work that up in tandem. And so that is being done through different components. We're looking at the social perspectives towards the approaches. We're also looking at the stakeholders, so the commercial entities and businesses who are looking to use that space. How do they perceive the different marine CDR techniques and how to communicate them? We are also working in governance structures, so looking at the legal, geopolitical implications, ethical questions, and sort of national and international jurisdiction frameworks. It's a very complex space. Unlike, to come back to those land-based analogies, if you stick it in your backyard, if you don't like it, you can always dig it up and get rid of it or deal with it in a different way. Once something's in the oceans, it could be out of your national jurisdiction very quickly in international space. So understanding what those implications are, how we can monitor and deal with it is vitally important for this sector. And sort of another component to that is actually the commercial entity space. There are a lot of companies in this area. We need to understand what they want to do. We understand what their barriers to implementation are, because if we don't work with them to understand what their gaps are, then they'll be operating a vacuum, the scientists will be operating a vacuum, the public will be having their knowledge from a vacuum, and really we need to bring all these components together. The final core theme of the project is about this implementation pathways and policy. So it's all about generating these policy briefs. Critically, to date, marine carbon dioxide pathways are not really incorporated in the integrated assessment models, which sort of underpin many of the IPCC type future climate scenarios. The ocean is poorly represented in that, so it's quite hard for us to sort of look at how we perturb, or if we change ocean carbonate chemistry, how would that then sort of filter through into future climate regulation? So that's something we're critically trying to evolve.
And are you focusing on any particular marine CDR process here, or are you kind of taking a whole scale approach?
It's absolutely whole scale. So we're trying to sort of boil it down to being as archetypal as possible, looking at biological versus chemical approaches. we will naturally have to have some case studies, and we're looking at those that are perhaps most developed, and quite uniquely, I'd say in this project, we are working hand in hand with companies. We're not trying to advocate for them in any way, shape or form, but we're trying to work with companies that are already at the process of doing small scale trials to say, what are you doing? Can we deploy our techniques? Can we understand the processes by which you've got to a point of doing a trial, so we can then sort of help that extrapolate out to other case scenarios, or inform other regulators that this is a guidance that works or might not work, and this is what the public responded to or didn't respond to in setting up that work. So this is something we're consciously trying to drive forwards. So we do have good connections with a few entities that are already running trials forthcoming in Europe. It's CO2 based in the Netherlands. So we'll be working with them to deploy some of the sensors developed here at the NOC to go and sort of see, one, how effective are the sensors that we have now, and you can go and buy them, you can deploy them. Are they good enough for monitoring carbon dioxide removal in this context? We also want to go and work with a company called Vesta, who are doing a similar, well, a very different approach, but looking at ocean alkalinity enhancement. They've got some trials happening in the US. There's other techniques, UK-based companies looking at the potential for seaweed growth and deposition. What do they do in terms of impacting deep sea environments? How effective are they at locking up the carbon and so forth? So there's lots of entities out there starting to run these pilot studies, these trials, and they are costly exercises. It takes a lot of money, and what we're seeing in the academic community, in the scientific community, in the regulatory community right now, is a need for all that information to come all at once. The time, unfortunately, for having kind of the science lead into the implementation in the policy is gone. It's all happening at tandem, and there's a real sort of jostling together all these needs for this information. So through CO2 CDR, we're trying to combine all those actors, everyone with an interest in space, to give them the information they need collectively.
So you mentioned just now there's a few kind of pilot studies underway kind of at the moment. Has anything been completed that is kind of shining any light on the potential effectiveness of this, or still super early to tell?
Unfortunately, it's still very early to tell. There have been some pilot studies done, and we do know that alkalinity enhancement is perhaps one of the most advanced. There's been a very, very successful trial run by Planetary in Halifax, Spain, in Canada. They are telling us that, perhaps unsurprisingly, the techniques do have capability to absorb carbon dioxide removal. We do see evidence for this happening, but it's perhaps not as effective as it might be possible. Things don't dissolve as quickly as might be anticipated. It might be harder to actually work out an air sea gradient flux, and we're going to have to incorporate that into models. There's natural variability in seawater chemistry, which we need to better understand. So all the trials that we are seeing today, as long as they're small scale constrained, which they are, then they have that capability to enhance our scientific understanding what could be done. I think importantly, the sector as a whole is not jumping in and going large scale. There is actually, as it sounds, an X Prize out there. Elon Musk is supporting this for up to $100 million. So it's a big scale carbon removal X Prize. There's stimulated a lot of interest and a lot of claims or potentials to say we can achieve this by the end of this decade. I think in the marine space, certainly we need to sort of just caveat that, saying techniques may have upscalable potential, but they can only achieve that once we understand what the scientific efficacy is, what the impacts would be, and give regulators, the public, and the decision makers the knowledge of what this is going to do. Because at the end of the day, carbon dioxide removal is a waste management strategy. We've been putting this waste into our atmospheres for decades. We need to now understand that we've got to put it somewhere else. And putting it somewhere else where it will have impacts. We got to understand what those impacts are, what the timeframes, what the severity is, because we're seeing those impacts on humanity now. And we're saying, well, we don't want that impact. We're seeing the impact on other ecosystems. So and we don't want that impact. But what level of impact is going to be okay? And who decides that? Right now, we're just trying to get the scientific evidence on which to enable those discussions to take place.
Absolutely. And I guess there's not really a one-size-fits-all scenario here. Different processes for marine CDR are going to be more or less effective in different parts of the global ocean, right? So it's not like someone does a pilot study for one particular process in this particular area, and then it's like, right, great, we can upscale that to the globe. That's not the case, is it?
Absolutely not. No. So I think we have to recognise that the ocean itself is highly variable. We have different temperatures of seawater. We have different organisms living in different places. We have different ocean currents that take things and move things around different speeds. I think recognizing how we interact with the ocean space and how the oceans interact with other spaces is going to be fundamentally important in terms of what goes where, when, and how. I think there's a big fear within the community that, the ocean is a big blue space. It will happen over the horizon. People won't know what's happening. It's going to be all done under the covers. In contrast, actually, what's happening today is people being very open, trying to do things in nearshore environments where public communities and the scientific community can actually measure and observe and see these changes happening. So it's likely that this will happen in these sort of environments to start off with. Again, that's there's Planetary's trial in Halifax and other trials here too, all happening in nearshore environments because we have that infrastructure.
Yeah, access.
Upscaling this is another question, and we can't just assume that we can go and do this and use all of the ocean surface to conduct marine CDR. It's not going to happen that way. We need to understand what can be done where, and starting small scale, giving us a little bit of scientific information is a route towards that.
Yeah, absolutely. And we've kind of touched on it a little bit, but I presume there are kind of knock-on impacts and risks associated with marine CDR. Can you tell us a bit about those?
Well, absolutely. And I can tell you that we're still trying to find out exactly what those risks are. Yeah. I mean, there's benefits. I think it's worth pointing out it's not all negative. We're doing this for a reason, but the main reason is to remove atmospheric CO2. But as part of that, we may find that there's other co-benefits that can be resulting from this. One area that I'm particularly active in right now is looking at sargassum management. And sargassum is an invasive seaweed. It's actually naturally occurs in the Sargasso Sea. Following a series of storm events driven by climate change, most likely in the 2010, 2011 timeframe, the sargassum sort of moved southwards in the Atlantic, has created a great Atlantic sargassum belt. And now that sargassum annually inundates the Caribbean countries, and it creates huge social, economic, environmental impacts when these tens of thousands of kilometers sized rafts of seaweed wash up onto the shorelines of the Caribbean region. That, although that's a direct impact of climate change on those communities, there is potential that actually, if we start to bury that seaweed in deep marine environments or deposit it on the sea floor, then actually that can help block away some of the carbon dioxide that's been trapped into that organisms, and at the same time, obviously, help protect those communities. So there are potential co-benefits. But of course, we need to understand what that sargassum, what that organic carbon would do to those deep marine environments before we can even consider or start implementing this. And that will then vary by region, by location, by depth, by what's down there. And again, to link this back to the terrestrial carbon dioxide removal approaches, we know that as we start these trials, what we expect to see in 1 or 2 years, it's not always necessarily the case. And actually it takes 4 or 5 maybe decades of worth of continual trials to actually fully understand what these techniques are doing. The concern is we don't have that time to start implementing some of these techniques if we're going to use them to realize our net zero technologies. So we have to start these trials now. We have to be doing the science hand in hand, potentially with implementation. And that can only start at a small scale controlled manner where we're gradually working this up to get our understanding in place. Yeah,
that's the only way to do it, I guess, isn't it?
Absolutely.
So what's next in store for CO2 CDR then? You said you're about 1.5 years in?
Yeah, we sort of got over that initial sort of initiation phase, and it's a really exciting couple of years planned. This is the point at which we start to deploy our sensors and start to get some data from those trials that we're starting to see initiated. We've already sort of spun up some models. We start to use those models in terms of extrapolating the potential for different techniques. We've already got some initial papers published in terms, or coming out shortly, in terms of our life cycle and technological impact assessment work. We're also in the phase of doing some of those engagements with the different communities of practice, or whether it's a public or commercial entities, really trying to understand what their perspectives are towards this, and really sort of building on trying to get our data out and get it out there to the community. So exciting couple of years ahead.
Yeah. And so how many more years have you got left on the project?
It's a 4-year project. So we've got three and a bit years still to go.
Amazing. Cool. Well, good luck with all of that anyway. Are there any other projects that you're working on related to this area of research?
Well, absolutely. So in terms of the sargassum deposition aspect I just referred to, so I've been working closely with Seafield Solutions and the University of West Indies to try and enhance our understanding of that, and in terms of the impacts that this would have on the deep sea communities. So we've actually already done a the baseline evaluation crew. So we already got some sites identified and assessed to enable us to do a sort of a very small scale, just a couple bales of sargassum deposition once the funding comes through. So we're kind of keeping our fingers crossed for that one, and very much on the looking at ocean alkalinity enhancement effects as well. So again, there's a few sort of ideas and projects in the pipeline for that. So
very exciting.
Trying to progress on all fronts simultaneously.
Yeah. Amazing. Well, good luck with all of that. Very, very important research. So I look forward to hearing more about that over the next few years. So closing question, do you see carbon dioxide removal as a game changer in tackling climate change?
To come back to the bath analogy, carbon dioxide removal will be essential, and it's already recognised our IPCC scenarios that we have to have this as part of the solution, but you have to turn off the taps first. So yes, once we start to reduce our fossil fuel emissions and greenhouse gas emissions, then yes, carbon dioxide removal will be part of the climate mitigation scenario. Absolutely. Marine carbon dioxide removal, I personally think, has to be part of this solution because the oceans are going to be doing this anyway, and the net effectiveness of those pumps means that we're going to have to look to the oceans in some shape or form. The big question, as we kind of discussed, is where, how much, and to what extent, and that will vary globally. So I think it's not right to sort of look at the oceans and say we're going to do one technique across all spaces and this is going to be what it is. I think we need to work collectively to better understand what's going to go where, and do that through small scale initiation studies. Really easily and openly share that data and enable us to sort of build it up forward. So I think it's going to happen. I think it's going to happen slowly. I hope it's going to happen slowly and incrementally, and hand in hand with good, sound scientific evidence. Yeah,
very important few years ahead of us then. Absolutely. And I guess time will tell. Well, anyway, thank you so much for taking part today.
A pleasure. Thank you.
We hope you enjoyed today's episode of the podcast. To ensure you don't miss out on future episodes, subscribe on Spotify, Apple Podcasts, YouTube, or wherever you listen to podcasts. See you next time.